All right, ladies and gentlemen, good morning. This video is covering parts of the atom as well as some atomic theory. And basically, this is actually geared towards a specific test, but there's a lot of good information that is in here, and as a result, would be very helpful to many, but I am going to have a study guide that is geared towards a specific test, so please excuse me ahead of time. First off, we're going to talk a little bit about atomic theory, okay? Dalton came up with the atomic theory. He developed the plum pudding model of the atom, and basically it almost looks like a ball with little things stuck in it, okay? But his atomic theory basically discusses four separate points. The first point is that atoms are the smallest part of an element. Okay, to expand that definition, atoms are the smallest part of an element that retain all of the properties of an element, and they can enter into chemical reactions. Okay, so if you look at an atom, it is as you know, and we're going to discuss in a little while, it is composed of three subatomic particles, protons, neutrons, and electrons. Okay, but the atom itself as a whole is the smallest part of an element that retains all of the properties of an element. So now, in addition to that, the parts of the atomic theory is that all matter is composed of atoms. Okay, everything in the universe, everything in the world, from air to the camera on this phone that is being used to record, this marker, you, me, the water, the food, everything is composed of atoms. Atoms cannot be divided, okay? They are very small, and each individual atom cannot be separated into a smaller component. All atoms of the same element are the same size. So all carbon atoms are the same size, all hydrogen atoms are the same size, all oxygen atoms are the same size. Every single element, their atoms are identical. And atoms of elements cannot change. So you cannot take an element and just add something to make another element. It doesn't work that way. Okay? So when you're looking at the elements of atoms, they are unique. They have their own unique structure, unique number of protons, which are the identity of the element, and we'll talk about that in a little bit. Okay, so just to kind of continue going on this section, looking at the Rutherford model, okay, Thomas Dalton had the plum pudding model, but the Rutherford gold foil experiment actually was able to dispute that, okay, or I'm sorry, Thomson's model. Rutherford was actually able to dispute the gold foil experiment. Through the gold foil experiment, he actually showed that there was a dense nucleus in the center of an atom, and that the surrounding area was mostly made up of empty space. So, we're going to talk a little bit about the structure of an atom. So looking here, you have, this is basically what one of the boxes on the periodic table looks like. So here you have your atomic number. This is your atomic symbol. The name. And this is your atomic mass in atomic mass units. Okay, AMU stands for atomic mass units. That's basically the measurement. Like you measure something in grams, the mass of atoms are measured in atomic mass units. So when you look at an atom, there are several parts to the atom. Okay, I'm going to show you the Bohr model, which you are familiar with. All right, and since we're working with carbon, I'm going to show you carbon. So you have the nucleus, which is composed of, let's say, make it a little bit easier, I like to make mine colorful, 1, 2, 3, 4, 5, 6 protons. And then we have 1, 2, 3, 4, 5, 6 neutrons. And then on the outside of the nucleus, you have the first shell, the first shell, excuse me, has 2 electrons. And then the second shell has a total of 1, 2, 3, 4 electrons for a total of 6 electrons. In a neutral atom, the number of electrons is equal to the number of protons. So since we have 6 protons in a neutral carbon atom, we have 6 electrons, 2 in the first shell and 4 in the second shell. So when we look at the Bohr model, and when we talk about the periodic table as well, I'm going to go a little bit into how the periodic table is structured. Okay, you have here columns. These columns represent groups. Okay, so here you have group 1, group 2. Now, there are several structures to the periodic table. The one that I like to use, it actually has 2 different numbering systems, the IUPAC numbering system at the top, and then a separate numbering system that separates the transition metals for the non-transition metals. So the non-transition metals here are listed as group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and then the regular IUPAC system is 1 through 18. I like to use the first one I mentioned is because if you separate the transitions from the non-transition metals, it makes it a little bit easier to understand when you get to bonding later on. So here you have groups 1, 2, 3, 4, 5, 6, 7, 8. Okay, those 8 groups are the non-transition metals, and then that's the 8A, 1 through 8A, and the 1 through 8B are the transition metals that are located in the center here. Okay? So, if you look at the periodic table, this information might not be needed yet, but the group numbers tell you how many electrons you have in the outer shell. So for example, carbon is in group 4A. It has 4 electrons in its outer shell. That information will come in handy later. But elements are grouped together based on having very similar properties. So all of group 1, for example, which are the alkali metals, they all have very similar properties. They're highly reactive. Group 2, very similar properties. They're also very reactive. And then group 3, 4, 5, 6, 7. Now group 7 also is very, very reactive. You have the halogens, which is group 7, okay? They tend to form diatomic molecules. I don't think you need to know that, but that's just one of their characteristics. All right, everything after 4, after carbon, tends to form negative electrons or negative ions because they gain electrons, and the first 3 groups 1, 2, and 3A, they tend to lose electrons and become positively charged. This group, the noble gases, they do not bond with anything at all. So these are the alkali metals, group 1. Alkaline earth metals is group 2. Group 7 is known as the halogens, and group 8 is known as the noble gases. The rest of the groups in the middle, they tend to be called the boron, carbon, and nitrogen families. And then the oxygen family has also been known as the chalogen family, halogen with a C in the front. These are all transition metals, and included with the transition metals are your inner transitions or lanthanide and actinide series. Okay, so that's pretty much how to read the periodic table. The periods go across, okay? And you see that the periods go by increasing atomic number from left to right. And They do tell a little bit about the atoms. They tell you how many electron shells you have. That'll come in handy later as well. So, looking to see what else you have to know. Talking about, oh, okay, so you were discussing the atomic, the way the periodic table is developed. Mendeleev developed the first periodic table, okay, and his structure was actually quite phenomenal. When he developed the first periodic table, he organized the periodic table according to increasing atomic number, but as he started to put elements together, he noticed that certain elements had similar properties. So although they went from left to right, according to increasing atomic number, he did organize them in columns or groups according to properties that are very similar, okay? He was actually able to use this to predict characteristics of elements that were never even discovered yet. One of my favorite ones that I look at is germanium. He used to call it ecosilicon, and that's because it appears below silicon on the periodic table. And he was right on the nose with its density. He was right on the nose with its color. He was within within very few degrees of its boiling points and melting points. He did an excellent job of predicting the characteristics of germanium. So the periodic table actually allowed him to determine what the characteristics of all of the unknown elements were. Okay, he was actually able to determine 3 of them in particular. So looking at metals, okay, the majority of the periodic table is made of metals. You have the alkali and alkaline earth metals, which are groups 1 and 2. I'm looking at my periodic table just so I can make sure I cover them all. And then you have your very large section in the middle, which are your transition metals, and then you have your post-transition metals and then metalloids. So a good chunk of your periodic table is composed of metals, okay? So 4 properties of metals: shininess or luster, conductivity, okay, ductility, as well as malleability, okay? Malleability is the ability to be able to mold, okay? That's why jewelry is usually made of metal, because although it's very strong, you can mold it into various shapes, okay? Ductility is actually very important. We use copper wire, for example. It's something we've been learning about in this class. We use copper wire, for example, to run through our electrical wires. We use it for conductivity because it's a great conductor of electricity. But one of the reasons it's so effective is because it can be created, it can be pulled into long, thin wires that can be run through our power cords, for example. So characteristics of metals and nonmetals, the groups that have characteristics, or the group that has characteristics of both metals and nonmetals, are metalloids, okay? And as I mentioned earlier, noble gases, they do not combine with anything at all, okay? They're the last group on the periodic table. Because their outer shells are full, they do not need to gain or lose electrons, and as a result, they're located on the outer shell. Okay, so what is the benefit of using certain elements? Well, when you're talking about radioactive elements, radioactive sounds kind of scary, but there's actually a lot of benefit to certain radioactive elements. One of the things we can do with radioactive elements is we can use them to date certain old objects. Okay, but they do give off radiation, so to a certain extent, there are radioactive elements that are very dangerous, and as a result, need to be handled very carefully. And in certain treatments, for example, cancer treatments, those radiation treatments have to be pinpointed to a very specific place so that they are targeting specifically the cells that you're looking to irradiate. Okay? So Um, when you're looking at radioactive isotopes, okay, tracers are used to determine some medical issues. So a tracer is run through and it can actually highlight certain abnormalities. And radiation therapy, as I recently mentioned, tends to, you can actually use it to destroy cancer cells. You can actually create a piece. I've actually seen this where they actually create a mold and there's a hole exactly where they want the laser to go, and that the radiation is actually passed right through that hole and it targets the cancer cells, so that when someone is undergoing treatment, their entire body is not exposed, but rather just the location that they want to irradiate. So at this point, it looks like I've covered just about everything on your review session, on your review sheet. Again, I do apologize for looking at the review sheet, but since I'm not the one teaching this, I want to make sure I covered all of your points. If you have any questions, please feel free to let me know. And tonight at 7:30, I will be on Twitch this evening doing a review session. You are welcome to join us if you want to log in and ask any questions. I'll be happy to answer your questions. I hope you guys have a fabulous day.